Alright, you guys, and now for number 9. It is pretty hard, it is pretty annoying, there is a nasty function, and there's an even nastier graph. But the good thing about this nasty exercise is that it tends to show up. And so, however hard it may be, you can prepare for it with a pretty good amount of certainty. So, at least in my experience, from what I've seen, there's quite a few exercises that talk about displacement, that talk about acceleration, that talk about velocity, all in one exercise. And so seeing how they are related to each other, how to go from one to the other, what it means by speed, distance, displacement, the differences between all of that, it is very, very relevant to be familiar with it so that you can get all of these points, which, by the way, are quite a few for just one exercise. So, that being said, for number 9, the context it gives us is that we have an object. It moves along a straight line and its velocity in meters per second. Okay, so its velocity v meters per second at time t seconds is given by this function here. And they tell you that this is for values of t that go from 0 to 4. Now, pop quiz. What is this? This, ladies and gentlemen, is what we will call our domain. What is the difference between domain and range? Intuitively, domain is like your possible x values, while your range, you guessed it, is your possible y values. And so my possible x values can only go from 0 to 4. Why do I know it's x values? Because this t that's shown here is in your x, it's in your horizontal. See? That's what I'm trying to say. And your y is going to be velocity. Okay, awesome. And so if it goes from 0 to 4, you know for a fact that over here you have a 0, and over here you have a 4. And so, again, this is just context, understanding like what's going on, okay? They tell us that the object first comes to rest at t equals k, and that the graph of v is shown in the following diagram. Now, because this is an object, moving along a straight line, correct? Then that means that when velocity equals 0, you guys, is when the object comes at a rest. So when it comes at a rest, it means that it's not moving. And so when is it not going to be moving? It's not moving if velocity equals 0. Now, velocity equaling 0 means that my, da, 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 it means that I am on my x-axis, right? Okay, that was not a good line. If velocity equals 0, that means you have a y of equals 0, and it means you have to be in your x-axis. And so not moving velocity equals 0 is right here. So, that's also something that's interesting. Your value of k is actually right there. So again, this is just understanding what they're giving at us at etc. See? So the graph of v is shown in the following diagram, and at t equals 0, the object is at the origin, it's where it starts, right? So it starts off with like a little bit of speed, right? So that's interesting. Maybe it's, I don't know, already falling or something, who knows, right? Anyways, for part A, we need to find the displacement of the object from the origin at t equals 1. And so here's something interesting. We're talking about displacement. There are two main concepts you have to get familiar with right away. One thing, oh, this is actually for later, so oops, spoilers. So one thing is what we call distance, okay? And the other thing is what we call displacement. Now, for all our intents and purposes, all you really have to know is that whether they ask for displacement or distance in your formula booklet, you have to keep that in mind because there's a formula for distance and there's a formula for displacement. So that's a quick rundown of like, okay, identify the buzzword, use the correct formula. So there's one for displacement, one for distance. They're a little bit different. See? Notice how the one for distance has these vertical lines, which is what we call absolute value. Okay? And so that is the only difference between the two. Distance is the same formula as displacement, but with absolute values. All right. An absolute value, all that it does, for example, absolute value of -3 gives you 3. An absolute value of -7 gives you 7. Okay. Absolute value of, I don't know, 4 stays as 4. So what's happening? It turns whatever's inside into a positive value. Okay, that's all it really does. All right, now that is like, in a more practical sense, what you need to know. So there's two formulas, identify the word, blah, blah, blah. Now over here, I'd like to explain that the difference between distance and displacement is the following. So imagine you start at point A, all right? You go to point B, okay? And you end up at point C, all right? And I'm just gonna make a bunch of different numbers up. So from A to B, it was, I don't know, 4 kilometers. From B to C, it was 2 kilometers. And that's that, right? And if I were to draw a line over here, or actually, before I talk about that, so from A to B was 4 kilometers. From B to C was 2 kilometers. And so distance traveled, right, is going to be 4 plus 2 gives you 6. All right, that's pretty straightforward. It makes sense. Now over here for displacement, I'm going to take the same exercise. So you have A going up to B and then going down to C, right? Now from A to B, it's still going to be the same 4 kilometers. From B to C is going to be the same 2 kilometers, but the displacement is a little bit different. And so from A to C, the distance here from A to C is going to be 5 kilometers. And so the displacement, you can think about it as like your effective distance, okay? And so your effective distance, what really matters is like start point to end point, all right? And so start point to end point, which is just going to be A to C, was 5 kilometers. So here displacement was 5, while distance does not care about distance from A to C. It only cares about the distance you actually covered. Okay, so that's the difference between distance and displacement. Displacement only cares about starting point and end point, while distance only cares about what you actually traveled step by step. All right, enough blah blah. Let's get into the exercise more into the thick of it. For part A, we need to find the displacement of the object from the origin at t equals 1. And so you identify the word displacement, you open up your formula booklet, and there is the formula you need to use. So let's understand it more thoroughly. So displacement is going to be the integral of t1 and t2 in respects to velocity and dt. Now that's a lot of not very intuitive math terms, okay? And I also didn't use like the fancy definitions, but that's because you don't need the fancy definitions. Who cares about the fancy definitions? What's really going on here, you guys, is that T1 is going to be like your starting point, okay? And T2 in this context is going to be your end point, all right? And all you need to do is plug in your velocity function and do the integral in respect to time, right? That's what's really happening. And so if I go ahead and sort of follow this formula, well, first let me write it down. So the formula was you go from T1 to T2, and we're taking our velocity formula, right, or function, and doing it in respects to dt, all right? So if I go ahead and plug this in, think about it. They want the displacement of the object from the origin at t equals 1. So if it's from the origin, that means that t1 is going to be 0 from the origin, while t equals 1 is literally just, okay, we're going to be finishing at t equals 1. Okay, so that's what it's telling you, and if you plug it in over here, you end up with integral of 0 up until 1, so it's from the origin until you reach 1 second, of vt. Now, Vt we know is negative t cubed plus 7 over 2t squared plus 2t, if I recall, minus 2t, sorry, plus 6. Minus 2t plus 6, and all of this is the integral in respect to dt. And so now I have it more set up, now it makes a little bit more sense. And so from here, well, how do you integrate this? Lo and behold, there's a lot of different stuff in your formula booklet, and even integrals include that. And so if you scroll up, you're eventually going to find the integral of x to the power of n, and surprise, it's the only integral you actually have to know. And yes, this looks nasty over here, but let me explain it just for a second, okay? So, keep the following in mind. Basically, really focus on what is happening to n. And so this n, on the one hand, is going to get added a plus 1 on top, and the exponent, whoops, and the exponent, which I want to put in a circle now, and so the exponent, right, will also go on the bottom. Oh, interesting. So if you have x squared, for example, and you do the integral of this, you are going to end up with, well, the x squared plus 1 divided by 2 plus 1. And you cannot forget this plus c. Now, what is plus c? Plus c is going to be a constant. All right, and why is a constant relevant? Well, let me explain it this way. So, much how in math you have plus being the opposite or the inverse, right, of negative, you have multiplication being the opposite of dividing, right? And you also have that, like, the derivative, basically. So I'm just going to write it. So derivative, its partner, right, its mirror, is going to be the integral. That means if you have, I don't know, x squared, and you do the derivative of this, you end up with 2x. But if you have 2x, and you do the integral of this, right, you're going to end up with x squared. Now, here's the interesting thing. Imagine I'm doing the same exercise, just that instead of x squared, you have x squared plus 420. So if you do the derivative of x squared plus 420, you end up with 2x. Whenever you do the derivative, the constant, boom, disappears. And so if you go from the integral of 2x and you do it, right, and you end up with x squared, well, lo and behold, where is my 420? It's always 420 somewhere, guys, by the way, just saying. So, where's my 420? And so that is why you need to put plus c, because technically there's a constant that you could have eliminated earlier through the derivative. Okay, that is why you put plus c. There could have been a constant that got eliminated from the derivative. That's the friendliest example I can give. Okay, so that is why there's a plus c. And last but not least, n cannot equal -1 because on the denominator you can't have it equal to 0. So whatever's on the bottom can't equal 0. So from here, n plus 1 cannot equal 0. It's the same as saying, by getting n alone, that n cannot equal -1. So, nothing too new there. You can't divide by 0. Anyways, that's just so that we understand how the integral actually works. But you can just follow, like, this formula step by step and it'll work out. See? So, that being said, you gotta do the integral of this whole thing. And don't get nervous. Plugging in the 1 and the 0, I'll show it in a second. Okay? But for now, leave it there. Don't touch it. And just do the integral, like, of the whole thing inside. Right? And so the integral of the whole thing inside, if you follow step by step, so on the one hand, right, well, there's negative t to the power of 3, you still have a negative that's just going to be sitting there. And then you're going to have t to the power of 3 plus 1. And on the bottom, you're going to have 3 plus 1. For this next term, you're going to end up with plus, well, the 7 over 2 is going to stay, so we're just going to leave it there for now, right? Times t to the power of 2 plus 1 divided by 2 plus 1. All right, interesting. Let me put this in parentheses because some of these fractions will end up interacting with each other, okay? For the next term, we end up with minus 2 times t to the power of 1 plus 1. 1 plus 1 because technically there is a 1 right here that's hidden, right? So t to the power of 1 plus 1 divided by 1 plus 1. And this last term, this 6, ends up being plus 6 times t to the power of 1 divided by 1. And this last one's a little bit weird, so let me explain. Technically, you guys, this last term, much how the one previous to it had a to the power of 1, this last one has a t to the power of 0. So t to the power of 0 equals 1, so it's legal to leave it that way. And you can think about it like, oh, so this is basically just 6 times 1, which is still 6, right? And so thinking about it in terms of t to the power of 0 helps you do this last step because, so basically what you're doing here, you're doing t to the power of 0 plus 1. And on the bottom, you're also doing 0 plus 1. All right? And so that is a way that you can sort of think about it. I think it's the best approach. I think it's the friendliest. Yada yada. Anyways, so that is just following this formula like to the heart, right? And so again, I still don't plug in 0 and 1. I'll get to that in a second. Don't stress out. But this is the heart of the integral. This is the hardest part, okay? And so once we did that, let's leave everything inside a little bit more pretty, right? Let's leave it a little bit more pretty. And so this first term, you can end up with negative t to the power of 4 divided by 4. This next one is going to end up being plus 7t cubed, right, divided by 2 times 3. And so 2 times 3 gives me 6. For this next term, I end up with minus 2 times, so minus 2 times t squared divided by 2. All right, so that's interesting. Plus 6t, quite literally, right? And so this third term here, you might have noticed, it has a 2 on the top, it has a 2 on the bottom, so you can go wablam, wablam, you end up with negative t squared, okay? Alright, you guys, and as I said, it's very important, I should have put it somewhere here, my bad, that you have a constant once you do the integral. So there should have been a plus c going around somewhere, right? Now you can apply sort of like the idea of the 0 and the 1. And what this is just going to do, okay, and it's always like this, is that you're going to have on the one side, on the left, you're first going to apply the bigger value. So for the 1, you're going to apply that. So you're going to apply t equals 1 first, right? So you end up with negative 1 to the power of 4 divided by 4 plus 7 to the power of 1 to the power of 3. 7 times 1 to the power of 3 divided by 6 minus 1 squared plus 6 times 1 plus c. And all of this is going to be minus, notice, it's going to be minus the side that is with t equals 0. But with t equals 0, it's a little bit troll because, if you plug in 0 here, that's going to disappear. If you plug in 0 here, that's going to disappear. If you plug in 0 here, that's going to disappear. If you plug in 0 here, that's going to disappear. But what is left? Plus c. And so this thing on the left, I'm just going to write it out so that we're on the same page, but it's really just 0 to the power of 4 divided by 4 plus 7 times 0 cubed divided by 6 minus 0 squared plus 6 times 0 plus c. And so really, if we work this out a little bit more, well, all of these will turn into 0 except for c. But you have a minus c. And so on the right side, you have minus c. All right. And on the left side, we end up with, well, this negative 1 to the power of 4 is just going to end up being negative 1 over 4 plus 7 over 6 minus 1 plus 6 plus c. And so plus c minus c, these go away. And now you end up with a bunch of fractions that you need to, well, see how they add up together and stuff and blah, blah, blah. And so from here, It's very annoying to work with fractions, but go piece by piece. And so I can put it as 7 over 6 plus 5 because of this, right? Minus 1 over 4, right? And so there's a lot of different ways to approach this. What I would suggest is first handling the 5, okay? And so handling the 5, I can combine it with the 7 over 6. And to do that, you need to amplify. And so when you add fractions, you need the same denominator. So you need the same number in the bottom. And so for this 5, what you can do is that you can do 5 times 6 over 6. And why is this legal? Well, 5 over 5, how much does it equal? It equals 1. 4 over 4, how much does it equal? It equals 1. 3 over 3, how much does it equal? It equals 1. And so it's legal to multiply by any of these because you're just multiplying by 1. And multiplying by 1 doesn't change your number, right? That is what we call amplification. So I'm amplifying the 5 over 1 by 6 by multiplying by 6 over 6, which is the same as multiplying by 1, right? I'm not actually changing the number. It just makes it more friendly for the fractions to work with each other. And so in this step, you end up with 7 over 6 plus 5 times 6 is 30 divided by 6. So, all this really was a way for these fractions to interact better. And so from here, you end up with 37 over 6 minus 1 over 4. And we're almost done. This is a little bit of an annoying part because now you need to find a way to make the denominators of 6 and 4 similar to each other, right? And so from here, what I would suggest is that you count the different multiples that each of them have and work from there. So for example, 6 has 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24. That's probably good enough. 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12. Already found a matching pair, and so I'm going to aim to amplify both so that the denominator equals 12. For the first one, for the 37 over 6, I need to amplify it by how much? By 2 over 2, because 6 times 2 is going to give me the 12. For the other one, for the minus 1 over 4, I need to amplify it by 3 over 3. And so 4 times 3 gives me the 12. Guys, just to be very clear, this is legal because 2 over 2 is equal to 1, so you're multiplying by 1, and 3 over 3 is also legal because it equals to 1. And so I just want to insist, all of this is legal because you're just multiplying by 1, okay? So the number on the left is 37 times 2, which is, with quick maths, you end up with 74 divided by 12 minus 3 divided by 12. And so from here, you end up with 71 over 12. And what are my units, you guys? My units are meters, right? And so your displacement for part A took a little bit to do, took a little bit of explaining, but I think we ended up with a very clear answer. For part A, it has to be the displacement 71 over 12 meters. I'm going to put it in blue just so that we remember that this was my final answer. So again, a lot of steps, but hey, it's worth 5 points, worth looking into it. So that is for part A. For part B, we need to find an expression for the acceleration of the object. And so now the big buzzword is acceleration. Now what do you have? You have velocity. So how can you reach acceleration from velocity? Now I'm sure that there's at least one of you saying, dude, I'm not a physics guy, like, don't ask me that, right? And some of the physics guys out there are already saying, dude, I know how to do that. And if you're an average Joe like me and you're not sure, what you are sure about is that the IB wants you to use the formula booklet. A lot of these exercises and a lot of people would do so much better if they just understood that the formula booklet has almost everything you need for the test. It is a massive hint for which formulas to use, for which procedure is the best to use for your approach, and etc. But it's only useful if you know what's in it. And so the moment you read acceleration, you should be thinking, I know that's somewhere in here. I know I've seen it. I'm not sure where. I'll find it. And once you do, bada bim, bada boom, there it is. And so acceleration, as you can see, on the one hand, is going to be the derivative of velocity in respects to time. And the one right next to it, if I recall correctly, is the derivative of speed twice in respect to time, twice. But the one we're interested in this case is just the first circle I put. And so basically, if you take velocity and do the derivative, you get acceleration. So just to be very clear, you have velocity. If you do the derivative, you're going to end up with acceleration. And I'm just saying, if you ever face an exercise that they give you acceleration and you need to reach velocity, well, you can reach velocity from acceleration by doing the integral, okay? So I'm just saying, I'm giving you knowledge because it might help out in the future, okay? What we're interested in for this step now is doing the derivative of velocity to reach acceleration. So for part B, what you can do is, well, I've explained a lot of things here. So for part B, what you can do is take your function, which we wrote down, well, it's the same one as this one here, right? And so it's negative t cubed. So velocity, right? Let me just write it again. See? So for part B, we have velocity equals negative t cubed, da da da, which is the same one up here, guys. Okay, so negative t cubed plus 7 over 2t squared plus 7 over 2t squared minus 2t plus 6, if I recall, is going to be my formula or function for velocity. All right, so this is the OG function for velocity. According to formula booklet, if I do the derivative of this in respect to time, I reach acceleration. So the derivative of this guy, which is going to give me acceleration, is just going to be the derivative of a bunch of exponents, right? And so the derivative of this, right, as you can see, you have a bunch of t's with exponents in them. And so the derivative you have to use, there's a lot of different ones you might have to use, right? For example, the tools they give you for derivative are of ln x, of the exponential, of cosine, of sine, but in this case, you're only interested in the one that's up here. And so the derivative of an exponent really just focus on the n. Okay, so the n on the one hand is going to go in front, multiplying, and we'll also get a negative 1 to its exponent. So for example, I don't know, x to the power of 4 is going to be, well, on the one hand, the 4 is going to go in front, and also you're going to have a 4 minus 1 up top. You end up with 4x to the power of 3. This gets juicy whenever you have fractions, but I'd rather just show you an action. Okay, so that was a quick example for derivative of an exponent. If I go over here for this first term, right, so this first term, technically there's a negative 1 here, okay? And so you end up with negative 1 times 3, because the exponent went down in front, times t to the power of 3 minus 1, because you need to do a minus 1 to your exponent. For this next one, you end up with plus 7 over 2 times 2 times t to the power of 2 minus 1, because you do negative 1 to the exponent. And this next one, the minus 2t, ends up with minus 2, because technically you had a 1 here and multiplied in front, and you ended up with t to the power of 1 minus 1, which is just going to be t to the power of 0. Just to be very complete in my approach, I'm going to put it here, okay? But technically the t is just going to disappear. And for this last one, as I said, technically there is a t to the power of 0, so that means that you end up with 6 times 0 times t to the power of 0 minus 1, right? And so this whole thing ends up being just 0 because there's a 0 multiplying it, right? That being said, my final sort of form for the acceleration, because I know I'm being very thorough with these steps, but just simplifying everything a little bit. This first one, you end up with negative 3, so negative 3t. The exponent is 2. This next one, the 2's go away with each other because of fractions. You end up with plus 7t to the power of 1. So you leave it like that. And this third one is minus 2 times t to the power of 0. Anything to the power of 0 is 1, so it's just minus 2. And this last term, already said, turns into 0, so you just leave it like that. This is your formula for acceleration. And so that is for part B. Let me write it over here in case we end up needing it. A of t is going to be, if I recall, negative 3t squared plus 7t minus 2. Okay? I'd like to make one quick observation, you guys. So, a lot of times what you need from part B was necessary. I mean, yeah, what you need in part B uh, is something you did in part A, right? But not always. This is an excellent example that maybe you have no idea how to do displacement. Maybe you opened the formula booklet, you saw the integral, and you said, "Nah, I can't do that." But hey, part B has nothing to do with part A, and it's just a derivative. And always claw for points wherever you can, right? So if the day of the test you're low on time and like you reach number 9 but you have 5 minutes left and you're like, dude, there's no way I'm doing part A, but you realize part B is just a derivative, do only part B. That's fine. You're gonna get 2 points and might as well get 2 points than 0, right? So again, just test taking skills. Be on the lookout for this kind of stuff. Here's an example where part B has nothing to do with part A. So you can just do part B and get 2 points and, better than nothing. Anyways, then for part C, they say hence. This is a massive hint. Whenever they say hence, without any more context, it's whatever you did from before, you need it for now. And so part C is an example that you need something from part B. You need something from part A. We're about to figure out what. So for part C, it says, find the greatest speed reached by the object before it comes to rest. Find the greatest speed reached by the object before it comes to rest. So think about it this way, right? I mean, mathematically, for part C, all I really need to tell you is that you take the derivative of velocity and you equal it to 0. All right, this is something you can memorize and you'll be good to go, but I'd rather explain it a little bit more intuitively. Imagine you're driving like a really fast car, see? And you're trying to see how fast it goes. And so you press on the pedal to the metal, and you go really fast, right? And I don't know, you reach, I'll make it up, like 180 kilometers per hour, like a crazy amount, right? And the moment you reach that, you stay there for like 5 seconds, and then you start decelerating because you're saying, damn, I'm going way too fast. See? The point is, when you were 5 seconds driving at 180, you weren't increasing your speed anymore, and you weren't decreasing it either. And so your acceleration at the greatest speed, you you held it there for a second. See? You held it there for a second, which is the whole point. So whenever you reach the maximum speed, acceleration is going to be 0. See? It's not so different than, like, I don't know, you're throwing like a ball. See? So you throw a ball that goes like this, like a parabola, and then it lands. See? And so as the ball is flying through the air, when it reaches its maximum like height, right? When it reaches the maximum height, it's not accelerating anymore because it's not going higher up. It's actually a speed of 0. It's frozen in the air for just a second, and then the speed goes negative. See? The same idea applies here. That is why velocity, you take its derivative and equal it to 0. Whenever you find, and this is the other great idea. So if you do derivative equals 0, you're looking for slope equals 0. See? And if you're looking for slope equals 0, you're looking for an optimization, a max or a min. Whenever your slope is 0, you are looking at a max or a minimum. So if you have a function that goes like this, actually no, let me make a better example. So example, a quadratic like that and another quadratic that goes like this. Think about the slopes, see? So the slope over here is positive, right? Let's say it's, I don't know, 2. The slope over here is also positive, and let's say it's like 1. But the slope over here at the maximum is how much? It's a flat line. The slope here is equal to 0. And so wherever the slope equals 0 is a max or a minimum. You can do the same exercise if you have something that looks like that for a minimum, right? I don't know why I drew 2 maximums. So for a minimum, it's the same idea. So this slope here is, I don't know, -2. Then this one is, I don't know, -1. And this last one is a slope of 0. And so wherever the slope of you have a slope of 0, you're finding the max or min. Here they're asking for greatest speed. And so on greatest speed means you gotta do the derivative of something equal to 0. Because it says hence, you gotta use something from before. So okay, get the acceleration and equal it to 0, right? And so here you did the derivative of velocity and you equaled it to 0. So you're finding wherever the acceleration equals 0. And for part C, you can take your acceleration formula from here and equal it to 0. And so a equals 0 is going to give you -3 t squared plus 7t minus 2 equals 0. And so from here, you need to find a way to solve for it. Now, technically, you have two approaches. On the one hand, from here, because it's the context of ax squared plus bx plus c, you have two main tools. One of them is what we call factoring, and the other one is what we call the quadratic formula. Now, I know that factoring is a little bit more fancy and is actually usually faster, but the quadratic formula is one that always works. And so I'd rather show you maybe the longer process, but the process that always works. So the quadratic formula, I think, is in here. There it is. So solutions of a quadratic equation is right here. See? And so as I was saying, whenever you have a context of a parabola equaling 0, which is exactly what's happening there, right? You can use this guy here. And so this guy here, what it gives you are the solutions for x, right? Where the whole thing equals 0, okay? Now, what is a, what is b, what is c? We'll take a closer look. A has an x squared next to it. B has an x to the power of 1 next to it. And C has nothing next to it, or, if you recall, an x to the power of 0 next to it. See? So remember how you want, but basically a, b, and c is defined by what x it has next to it. See? So if it's x squared, it's going to be a. If it's x to the power of 1, it's going to be b. If it's x to the power of 0, it's going to be c. So from here, be very, very organized in your approach. And I suggest take a moment, write down what a is, what b is, what c is. So a in this context is -3, b in this context is 7, and c in this context is -2. What was my formula? My formula from here is going to be -b plus or minus square root of b squared minus 4ac divided by 2a. So you plug all of this in into that formula here. What you end up with is -7 plus or minus square root of 7 squared minus 4 times -3 times -2 divided by 2 to the power of a, which is -3. And so -7 plus or minus square root of 49 minus 4 times 3 gives me 12, times 2 gives me 24, divided by 2 times -3 gives me -6. So from here you end up with -7 plus or minus square root of 25, because 49 minus 24, divided by -6. So -7 plus or minus 5 divided by -6. So you from here, you're almost done. See? From here, the weird thing that's going on is that you have a plus or minus. So what the heck does plus or minus do? Exactly what I'm telling you. It's plus or minus. So you're going to have one answer that is plus, or the other one, which is minus. And usually, depending by context, it's pretty obvious like which one you take. But I'll explain in a second how that applies here. And so up here, I can do -7 plus 5 divided by -6. And for the other one, you can do -7 minus 5 divided by negative, whoops, divided by negative 6. And so this one up top ends up being negative 2 divided by negative 6. And this other one ends up being negative 12 divided by negative 6. So this one up top is going to be positive 1 over 3. And this one on the bottom is going to be positive 2. And so basically what it's saying here is that you reach, okay, a maximum. Here's the thing. Let me be a little bit more clear. So the greatest speed is reached at t equals 1 over 3 or t equals 2. Now here's the thing. You don't know if this is a maximum or a minimum. You just know that these are optimization points, okay? And so the greatest speed is either at t equals 1/3 or t equals 2, okay? That is sort of like the main idea, okay? That is sort of like the main idea. And so from here, what you gotta do is plug in t equals 1 over 3 into one of your formulas to see what like speed you get, right? And t equals 2 as well to see what speed you get. And so you can plug in into your velocity formula 1 over 3, and you can also plug in into your velocity formula the value of 2, see which one is bigger, and work from there. So if you plug in 1 over 3, you end up with negative 1 over 3 cubed plus 7 over 2, 1 over 3 squared, right? Minus 2 times 1 over 3 plus 6. And if you plug in 2, you end up with negative 2 cubed plus 7 over 2, 2 squared, minus 2 times 2 plus 6. And so this one up top, as you can see, ends up being negative 1 over 27 plus 7 divided by 9 minus 2 over 3. Now let me make a little bit of space here, so this point is k plus 6, right? While the one on the bottom ends up being negative 2, 4, 8, so negative 8 plus, this is times 4, so you end up with 28 divided by 2 minus 4 plus 6. And so from here, you kind of have to tell which one is bigger, right? Which one seems bigger, which one should be bigger, etc. And so right off the bat, you actually can say that the one on the bottom is a little bit bigger because 28 divided by 2, you can simplify it immediately. And this gives you positive 14. And so damn, basically, from here, you end up with 14 plus 6 gives 20, minus the 8 and the 4 is minus 12. You end up with a velocity or speed of 8. While this one up top, do you think you get anywhere close to 8? Think about it. You have a 6 plus a 7 over 9, which is a little less than 1. So I don't know, imagine it as like 0.8, okay? And you have minus 2/3, which is minus 0.66, and minus 1 over 27, which is like minus 0.01. Again, I'm just making some of these numbers up. This one is legit. But I'm making some of these numbers up just so that we understand the magnitude of the numbers. And you can immediately tell, yeah, velocity of 2 is going to be way bigger than velocity of 1/3. Okay? Another way that can sort of make sense is that you're substituting the larger possible t value into velocity, right? That one's a little more debatable, but I'd rather show the full process. You can compare both, and eventually you realize up top you have a bunch of fractions. On the bottom you have bigger whole numbers, okay? And so your answer here was 8. And so for part C, plugging in t equals 2, you end up with uh, da, 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 speed of 8 meters per per second, right? Because those are the units that we're working with here. So again, I would like to do the observation that for part C, the amount of points was 5. So definitely more time taking, definitely harder. If you feel frustrated, it's pretty normal. Part C is hard. Okay, I want to give you the tranquility that this stuff is not easy. All right, but the fact that you're watching this video and putting the effort goes to show it's gonna pay off. So keep it up. All right, whatever you're doing, keep it up. You got this. Don't give up. For part D, we need to find the greatest speed reached by the object for the time between 0 and 4. And so here it might be a little bit confusing. And so you really need to understand, like, what's the catch, right? And so on the one hand, I already told you that we found the greatest speed. And so we found the two optimals, which was at t equals 1/3 or at t equals 2. But the thing is, that was... here's the thing. I think this is the best way to explain it. So, um, even up here, it's pretty explainable. So I'll do it here. See? So if you look at your graph, right? If you look at your graph, what you ended up with, or what they told you, right? What you ended up with is discovering that you have 2 points of optimization, right? So you found 2 points of optimization. You found one that was at t equals 1/3, and you found another one, correct? You found another one that was at t equals 2, right? So if you look at 1/3, you can see that this is a point of optimization because it's a minimum. And at t equals 2, which is around here, well, it makes sense. You end up with a maximum, right? And so here's the 1/3, here's the 2. It makes sense. There's a min, there's a max. That's why it showed up when I did the derivative, right? I was asking my function, yo, where's my slope equal to 0? And it's exactly at 1/3 and at 2. But the thing that we need to keep in mind with this idea is that although this can be a min and this can be a max, technically our highest possible sort of value or velocity can also be elsewhere. Now, what do I mean by this? Example, imagine you have a function that looks, I don't know, something like this, okay? And it's restricted. So you see, when I put those circles there, it means it's restricted. That is as far as it goes. And so if I go ahead and ask you, okay, like, where's the minimum? Some of you would say this, but technically your minimum value is this guy here. And so it's very important, and this is the main idea, it's very important that you consider plugging in, how should I say it? Plugging in boundary values, okay? Because you might find the minimum by doing the derivative and all of that stuff, but for finding the actual lowest value, or, the other way around, the actual greatest value, you need to plug in the boundary values, see? And now this that I did here for 1/3 and 2 and all that stuff is just a very visual appeal for this. But technically all you really need to do is plug in the boundary values and see if there's something there that beats the maximum you reached earlier, because it might be a scenario like this one here, right? Yes, you have a minimum right there, but your actual minimum value is this, right? Yes, you have, maximum, right? I'm not explaining myself well, but I think it'll eventually make sense. So let me go over it one more time. See? This is like a key point, right? As a maximum, but its lowest actual value is this here. See? So if I were actually, now I'm going to nail the explanation. See? The reason you need to plug in boundary values, and again, sorry for not explaining it well the first time, but the reason for plugging in boundary values is that you can have a function that looks like this. You can have something that goes boom, boom, boom. Okay? And so, yes, you have a max here and you have a min here, but technically, this would be what we call a local max, and this is a local min. It's like one of the minimums, one of the maximums. But the actual minimum is this guy here. So this would be your global minimum, okay? And this over here would be your global maximum. And so yes, what happened over here is that we found the greatest speed reached by the object before it comes to a rest. So it's like before k. So it's the maximums over here. But technically you need to plug in the boundary values because this value can also be very big. See? And now you might be thinking, isn't that a negative value? And I say, careful. We're talking about velocity. So if you have a very big negative velocity, it means, for example, you're driving your car. So here you're like going forward, right? Technically, sort of. You can think about it that way for now. And over here, you're going in reverse. But maybe you're going way faster in reverse than you ever went forward. All right, anyways, that was a lot of blah blah. I hope I cleared up some ideas. But for part D, the greatest speed reached by the object from 0 to t to 4, you gotta plug in the boundary values. And so plugging in 0 doesn't make sense, because if you plug in 0 here, well, I mean, it might make sense, but if you plug in 0 here, this goes away with this, goes away with this, you end up with just plus 6. And so one of our maximums that we already found was a speed of 8. So unless we find something greater than 8, it's not worth it. So now let's try plugging in 4. If you try plugging in 4, what you end up with is negative 4 to the power of 3 plus 7 over 2, 4 squared minus 2 times 4 plus 6. And so v to the power of 4, v of 4 is going to give you negative, that is 4 times 4 is 16, times 4 is 64, so negative 64, plus 4 times 4 is 16, so it's going to be 7 times 16 divided by 2, minus 8 plus 6. And so, oof, I end up with pretty big numbers. Let's see what happens here. So negative 64 plus, and for this next one, right, this is just a quick sort of tip for simplifying fractions, but because you have a 2 on the bottom, it'd be pretty convenient if you had a 2 on top. So you can rewrite the 16 as 8 times 2 divided by 2 minus 8 plus 6. Why is that useful? Because now you can do boom, boom. That goes away with that. So now I can start combining like terms. You end up with the minus 64 minus 8 and the plus 6 plus 7 times 8. And 7 times 8 is going to give me, 8 times 8 is 64. So minus 8 gives me 56 plus 56. And so from here you can combine all of this. You end up with 56 plus 6 should be giving me 62 minus 64 minus 8, which is a pretty big value. So give me a moment. That gives me minus. Wow, I cannot do math today. You're never alone in your math troubles. So this gives you 62 minus 72. All right, so you end up with minus 10. And so the greatest speed, this is the thing. So if your velocity is negative 10, that means you're going like backwards in your car, negative 10 miles per hour. So your speed is 10. Think about it that way. Speed is always like thinking in terms of absolute value. Okay? And so in terms of absolute value, your speed was 10. Yes, yes, it's negative, but it's because you were going backwards. And so from here, the greatest speed reached, because the velocity gave you negative 10, you can say, I was going backwards 10 meters per second. So the greatest speed reached at t equals 4 ended up being 10 meters per second. All right? So think about it that way. That is for part D. And now part E, which is kind of crazy. They ask us to write down an expression that represents the distance traveled by the object while its speed, and notice, while its speed is increasing. Do not evaluate the expression. So this is more of a context problem, to be honest. It's a little bit more of a context problem. You need to understand when the object when is the object traveling with its speed increasing? And so, well, this is pretty hard, but I'll try to explain it the best I can. So let me make a little bit of space here. See? So this is the last part of the exercise. You already have a lot of context of how the object behaves, where the maximums were, where the minimums were, blah, 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 blah. And the point is that you need to identify where the speed is increasing. And so this also has to do with understanding velocity, okay? And so you have to understand velocity in different ways when you have positive velocity and when you have negative velocity, okay? When you have negative velocity, think about it as like you're going backwards. Okay, but if you're going backwards, your speed is still up, right? Think about a car going like, think about it this way. If you're in a car and you're going backwards, but you're going faster each time, it's like you're going backwards, but you have your pedal to the metal, then your speed is getting higher. And so having that in mind, well, where is my speed increasing and my distance as well? We'll only focus on speed increasing. And so here we said we had a minimum that was at 1/3 and a maximum at 2. And so immediately you can say, so there is a speed increasing here. See? So one of your intervals is going to be this one, right? But technically from part D, you did just discover something very interesting. So from part D, you discovered that at equals 4, you have a speed of 10. So that means that at some point, you were going 10 meters per second backwards. Okay? Interesting. And so was I ever stopped in between? Well, what was K again? Oh, K is when the object first comes to a rest. So at K, you are not moving, and then you start going backwards. Okay? So think about it this way. It's like the ball, right? Or even a car, right? So it's like you're a car, see? And you're driving, yada, 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 yada. And you really wanted to go to Wendy's because you love Wendy's. It's the best burger place in the world. Double Baconator is one of the finer burgers and inventions humankind has ever done. And so you want to go to Wendy's, right? And so you're driving, and oops, you realize you went too far, right? You passed the Wendy's, right? Sacrilege. You passed the Wendy's, and so you hit the brakes. So think about it this way: you're going. You pass the Wendy's, and so you hit the brakes. Boom, and eventually you're stopped. And then you start going backwards in reverse, and your speed gains up again. That is what's happening. See? That is what's happening. And so technically, you can also say that from here to here, from braking and going in reverse, your speed is also increasing. And so the two intervals that you're worried about or that concern you is what I have in red. So technically, speed increases, and this is not my final answer, but just intuitively. So speed increases from 1/3 to 2 and from K, which is the stopping point, to 4, right? So K and 4 and 1/3 and 2, okay? So this is what I need to put in like fancy sort of math language, right? But the idea where you understood it. So you're driving and you have a certain amount of speed. You pass the Wendy's, so you hit the brakes, and while you hit the brakes, velocity is dropping. Eventually you stop and you start going in reverse, right? Really focus on when speed is increasing. That is the main idea, all right? So speed increases from 1/3 to 2 and from K to 4. That being said, writing down the expression that evaluates the distance traveled, so here's another buzzword we're talking about. Look at that. Distance. So remember a million years ago I talked about the difference between distance and displacement, well, identifying the word distance is again a massive hint for you to go to the formula booklet and looking for distance. And once you find distance, you're going to see, oh, okay, so distance is going to be the absolute value of my terms from the starting point to the end point. Now you have two different intervals, right? You have from 1/3 to 2 and from k to 4. And so technically from here, you need to express it with like the following idea, okay? You need to think about it as, well, first of all, you identify the intervals where the speed increases, right? And now, because you need to express it as distance, right? And now because you need to express it as distance, what you can think about it is that it's going to be basically the integral, right? Of the part that is positive, so everything that's up here, right? And so for the part that is positive, everything that's up here, which is just this section there, the part that's positive does not need an absolute value. So you can just say for this first section, okay, the part that I'm putting now in green is going to be from 1/3 up until 2 of your velocity function in respect to dt, right? Plus the integral of the negative portion. And so the negative portion needs to be an absolute value because you only care about when speed is increasing. You don't care that you're going backwards, right? And so this will have the absolute value of your Vt in respect to dt. And its starting point, as we said, is going to be k, and it will finish at 4. How do you know it finishes at 4? Because your domain was restricted all along to be until 4. Okay? So, ladies and gentlemen, this was quite an intense problem, I'm not gonna lie. But if there's one good thing about it, as I said way in the beginning, is that it tends to show up. So might as well get familiar with velocity, might as well get familiar with these formulas, and if there's something I can say is that the approach is usually like pretty similar. Like you usually they usually give you one of these, and you gotta jump from one to the other. Okay, and so that is one thing you need to keep in mind. Just integrals and derivatives. If you're not sure or forget how they were, remember it's in your formula booklet. Okay, the derivative of an exponent, the integral of an exponent is all right here. I know these formulas look scary, but think about it in terms of examples. So maybe just learn one example like really well, and you can apply that logic everywhere, and it's gonna be much more friendly. Guys, at the end of the day, it's making the formula booklet friendly, okay? A lot of people, as I say, like take it for granted. Come on, I have the formula booklet the day of the test, so like whatever. It's like an answer key, like I'm good. But what does it help you to have the formulas if you don't understand how they work? What's the most efficient way to use them? What's actually in it? So study with the formula booklet, you guys. Do it. You can do really well if you get familiar with it. I assure you. That, ladies and gentlemen, is how you solve for number 9. I hope it helped.